Now, I think that at this stage, the best thing is to make an example of application. And I propose there is an example of application that is presented in my notes. They are already online. And basically, yeah, please. Basically, the example of application says, let us suppose that a record of 10 annual maxima is available. So 10 years. Observation period, 10 years. And including the following observations. And you have the list of the observations there. And one is required to estimate the 5-year return period peak flow. Okay? And let me, first of all, make some considerations. Because I want to make over an Excel sheet this computation by using the relationships that you see here, so we can also see if they are correct. Okay? And then my proposal is, once that we completed the exercise with these relationships, let's try with the relationship presented by Wikipedia and see if we get the same result. Okay? So, a couple of considerations before I start. First of all, please try to observe even in this case. Basically, what I'm presenting here is 10 annual maxima, and I said observation period 10 years. So get familiar with the terms. 10 annual maxima means 10 years, and the 10 years is what I call the observation period. Okay? And the return period is 5 years proposed. You may say, but so far you talked about 100 years, 200 years, why now only 5 years? Please start to look at the relationship between the number, capital N, of observations and the return period. It's lower. The return period is lower than the number of observations. I anticipate this, that this would be a kind of rule of thumb. Not exceed with the return period, not to exceed with the return period, the number of observations, if possible. Why is that? Because look at the physical process. You observe a process for 10 years. Okay, so basically your window, your observation window is 10 years. And let's suppose that now you want to estimate the river flow, which is exceeded on average once every 100 years. Is it reasonable? You observe a process for 10 years, and then you pretend that you have gained a knowledge that allows you to say, I know what happens once in 100 years. This is not reasonable. It's not reasonable, okay? If you observe the process for 10 years, it's reasonable that you say, let me predict what happens once in every 5 years. Because your observations include that value. We will see that when we get the estimate of the 5 years return period flow, it is included in the range covered by the observations. Instead, if I tried to estimate the river flow for a return period of 100 years, I would get an estimate. We will make this attempt, an estimate that is outside the range covered by the observations. So basically, you are outside the picture that you gained by observing. This is not reasonable. Okay? Every time that you extrapolate in engineering, you must be careful. Okay, now let me take these observations. Let me copy them on Excel. Okay, so I do like that. And let me open an Excel sheet, enlarge it. And let me now do that. Sorry, I need to separate these data because they are now in Excel. I copied it like a text. I need to separate it. And okay, and then it's better for me if I put them, they are now in columns, it's better if I put them in rows. So let me copy these numbers and paste them, sorry. Okay, I see. Just 1 second. Okay, these are the numbers I need to. These are my annual maxima. Perfect. And let me compute. Let me do like this. I copy them here. And let me compute the average. And the average is just, I'm sorry it is in Italian, my Excel, but it's, there is an Excel function which computes the average, okay? And there is also the standard deviation. Let me do like that. I think should be, I don't remember, so let me do like this. I don't remember the name of, there is a function in Excel computing the standard deviation, I don't remember it. And I computed it as a square root of the variance. The variance is the squared standard deviation. So basically this is the average and this is the standard deviation. So this is, let me call it M equal 2 and this is sigma equal 2, okay? And now I can compute beta equal to, so beta is plus sigma divided by 1.283 and now mu is equal to M minus 0.45 times sigma. Okay, this should be, let me see, M is, okay, yeah, should work. Okay, perfect. And now the return period is, or let me just write t equal to 5, okay? Now, what I need now is to write this relationship here. So x equal to, and I don't remember, let me see. I think the function in Excel is log. Yeah, first of all, let me minus data times log. Yeah, log is the logarithm with base e is log in Excel, and so it is minus beta log, and it's. I open another square parenthesis, is t minus 1 divided by t. Should work. Sorry. And
should be the opposite, t over t minus 1.
Yeah, correct, thank you. And I need to shift the parenthesis 1 second. Now should work. Okay. And plus me, correct. Plus 2 plus me. Okay. So now this is the number. So look at the estimate, and look at the data. And let me just, I hope it's still visible. I would like to visualize the estimate together with the data. Can you see the screen? Okay. So the estimate is 3.81, and let's look at the data now. First of all, how many times we do expect to see the occurrence of a 5-year return period flood in 10 years. On average, we would expect to see it twice, okay? So let's look at the data. How many times did we see a comparable estimate? 486, 1, 500, 2, 384, 3. So you see that it's reasonable. Sorry, okay, 408. It's the fourth. It's reasonable, okay? It's reasonable. Now let's try to put 10 years. 408, which is exceeded by 486, and it is exceeded twice, so it's reasonable. And why I say it's reasonable, you may say, no, I would expect to match the number. You could match the number if the probability distribution is fitting the data perfectly, but it's not, this is not still checked. So, but still, you see that it's comparable. If you found here, because if you look at the highest number is 508. So you have this number is lower than 20%. 20% is 5. So if you found, of course, something like a huge difference, then you may get in doubt. And let's now see what happens if I put here 100 years. 100 years, I'm still not extrapolating. If I put 1,000, I am extrapolating already. You see? So I think it is reasonable. And so this is the result that I wanted to get. Okay. You see that it's very simple. Now, let's try to make an experiment by computing, by using the Wikipedia relationship now, okay? So let me put x equal to, this is an experiment that I'm doing online with you. Let's see what happens, okay? And let's suppose that the parameters have the same meaning. I'm not sure of that, because it's a different way of writing. Maybe that the parameters have a different meaning. But let me try now just an attempt with the same meaning of the parameter to see what happens. And first of all, let me point out one thing. Let's make some physical consideration. What do we expect from this relationship? We expect that the probability of not exceedance for increasing, let me write it again in the form of the probability of not exceedance. Px is equal to E minus x minus me divided by beta. So what happens if here, if x tends to infinity? I would expect that the probability of not exceedance tends to 1. Let's see if this happens. If x tends to infinity, we get e to the power of minus infinity here, and so this would tend to 0. E to the power of 0 is 1. So indeed this relationship from a basic physical consideration seems to be reliable. Now let's make the same analysis, physical analysis, rough physical analysis with the Wikipedia relationship, which is here. So does this tend to 1 if x, let me just enlarge it a bit. If x tends to infinity. So if x tends to infinity, here we have e to the power of minus infinity, and therefore this would be e to the power of infinity, sorry. This would be e to minus infinity, to the power of minus infinity, which means 0, tends to 1. This also tends to 1. Okay, let's now try to apply this relationship by, we need to invert it still. And but anyway, let me try to estimate the probability for by placing an x value. So let me go to the Excel sheet. And let's suppose that I want to calculate the probability for this x value, okay? Because in this way I avoid to invert this relationship. So the probability is, according to Wikipedia, it's F 301 died 92 is equal to. So this is, let me read again because I don't remember my memory, equal 1 minus, and it's exp of minus exp, sorry, minus exp of, I need to jump back and forth, sorry for that. So it's x minus me divided by beta, okay? So this would be x minus me. I need to put a parenthesis here, divided by beta, and I need to put a parenthesis here. And this should be it. Let me see. Okay, this should be it. No. Okay, let me see if everything is correct. 1 minus exp b18 minus b15, which is me, divided by beta. Should work. And now let me compute f, again with my relationship. My relationship would be plus exp of minus exp minus it's x minus me divided by beta. Okay, okay. No, it's different. Oh yeah, sorry once again. It's this is strange. B18 minus B15 divided B14. Okay. Divided, yeah. Okay, so okay, let me postpone this check to tomorrow morning, okay? Because I think I made some mistake in the computation, but we can't lose time to check where I made the mistake. I think I made some mistake here because it's impossible that we get a probability of not exceedance of 0.69 while I just inverted the equation, so it's not possible because I started from a probability of not exceedance which is probably, okay, let me just check it and tomorrow morning we will check. I think the writing is equivalent, but this is a doubt that we resolve tomorrow morning. Okay, sorry for that, but as I said, I didn't notice that it was written in a different way. Okay, so basically, this is then the example of application. And by the way, I think the estimate that I got here, yeah, there is some computation error because the estimate that I got here is a bit higher than the estimate that I got in the Excel file. So let me just remake this tomorrow. And now let me move to the next step, which is the verification of the fit, okay? What is here the purpose? The purpose is to check if the probability distribution that we used, the Campbell distribution, provides a good estimate of the probability of not exceedance of the data. And in order to make this check, we need to introduce a statistical test, which may seem something that is a bit boring to you, but indeed it is a very simple check. And the check is based on keeping in mind that the probability of not exceedance should be a good estimate of the frequency of not exceedance. If the probability distribution is fitting the data well, then the probability distribution provides an estimate for the probability of not exceedance, which should match the frequency of not exceedance. But the frequency of not exceedance can be easily estimated from the data without any assumption, without any statistical computation. How to compute the probability of not exceedance, sorry, the frequency of not exceedance of observed data. And let me get back to the example that I gave to you. So let me get these numbers. These numbers that you see up there. Let's compute for these numbers the frequency of not exceedance. And in order to do that, what I need to do is to write the numbers in ascending order, increasing numbers. So what is the minimum here? The minimum, I think, is 184. So this is the lowest, 184. That's 0. And this is, I put a rank of 1. In an ascending order, this observation has rank 1. Okay, the second one is, I think it is 239. So second, 239, that's 0. The third should be 271. Let me check, because, you know, I'm just moving online. So 271, yes, I think it is fine. And now the fourth should be 315. 315, that's 0. And then the fifth, let me see, 315, 335, correct? Let me see, yes, 335 and then 370. So 335, 370, and if I'm not wrong, is 384. And then 384 is correct, yes, and then 408, and the next one is 486. So 408, 9, 486, and finally 10 is 508, is if I well remember. Okay. 10 observations in increasing order. So, with the rank here. How many times was not exceeded this number? So this number was not exceeded only one time, okay? Because for all the other occurrences, it was exceeded. So 148 was not exceeded only one time, which is the rank here. The rank indicates the number of not exceedances. In order to compute the frequency, we have to divide the number of not exceedances by the total number of numbers, the total number of outcomes. So this has frequency of not exceedance of 110. This has 210. And so forth. And this is 10 by 10. Okay? But there is to say that the literature tells us in order to take a safety factor to divide by capital N plus 1. Okay? And then here again capital N plus 1, and here again capital N plus 1. So 11. Why is that? Because for the highest one, in doing that, you avoid to get an estimate of frequency of not exceedance equal to 1. And this would be physically incorrect. If you ended up with an estimate of the frequency of not exceedance for the highest one of 1, it wouldn't be correct. Why is that? Because you would implicitly assume that this number, which is only the highest in 10, has a frequency of not exceedance of 1, which means that this would be the maximum that you expect in a probabilistic sense. This wouldn't be correct. Because you have only 10 observations, you have to admit that in the future you may have highest outcomes. And therefore you need to assume that the frequency of not exceedance of the highest observation is lower than 1. Is it clear for this concept? You can't say that an observation, the highest observation in your observation period, and the observation period is finite, so it doesn't give you an overall picture of the process. You can't assume that the highest has a frequency of not exceedance of 1, because you would implicitly assume that this is the highest number that you expect forever, which is not correct, because your observation period is only a partial picture. Okay, so the literature says increase the denominator by 1 to avoid to get an estimate of the frequency of 1. But otherwise, it's very clear that this easy computation provides you an estimate of the frequency of not exceedance. And look, this addition of 1 becomes negligible for increasing capital N, which is what you would expect, because for increasing window, for increasing observation period, you get a picture that becomes more and more reliable. And therefore the impact of this safety factor becomes negligible. Okay, so this is your frequency of not exceedance. Now, the idea of the statistical test is to compute the difference between the frequency of not exceedance, let me call it capital Fx, which is just computed on the data. It's only a data analysis. Let's compute the difference between the frequency of not exceedance and the probability of not exceedance given by the Gamble distribution. So this is given by the Gamble and this is given by the data. So it's intuition, it's your intuition, it's intuitive that if the Gamble distribution is working well, it should approximate the frequency of not exceedance, and this difference should become negligible. And let's compute it in absolute value and say that this has to be lower than some statistics. So lower than something that I may call, what it's called here, it's called dn. No, let me see. It's not dn, but it's k. It's lower than something that is called with k. And look, this difference can be computed for all the data. So for each of these outcomes, you can apply the Gamble distribution, compute the probability for each of these outcomes, compute the related frequency of not exceedance according to this computation that I showed here, and you can compute the difference. And if the distribution is reliable over the whole range, you should always get that this difference between probability and frequency is lower than a given k. So basically what we do in the statistical test, in order to be safe, we take the max here. We take the max of this statistics and we check that is lower by a given k. And this is what is done here in this. Let me see if I have the picture. No, it was, yeah, here. In this picture, you see, this is x, this is probability, the red line, this is frequency of not exceedance, and you take the larger difference. It's very easy. We will make an exercise tomorrow on this. Tomorrow we will take these 10 numbers and together we will make the computation of the flood peak, and we will check with the Kolmogorov test with R that everything is fine. Okay. And now the only piece that is missing to you is how to compute K. And K is just given by tables. It is provided by the literature in tables. And I would like to tell you that usually we assume that K is equal to 1.36 divided by square root of m. And that's it. Okay, now we are all set. Okay, and what happens if the test is not satisfied? If the test is not satisfied, we simply have to change the probability distribution. And here the notes tell you some suggestions of alternative distributions, and we don't spend time on studying these alternative distributions because you know, the concepts are the same. The concepts are equivalent. It just changes the analytical relationship describing the probability distribution, the shape of the probability distribution, and it just changes the number of parameters and how to estimate them. Basically, in most of the cases, it has been proved that the Gambit distribution works well, also because of the test that I introduced here, which is the Kolmogorov-Smirnov test. It's called the Kolmogorov-Smirnov. It's not very severe. And therefore, you know, it's very frequently passed. And that's it. The only thing that is missing, but we will explore tomorrow, is to check the consistency of my writing with Wikipedia ones. And there is a final discussion that I would like to make, and which is just some thoughts on the concepts here. Basically, what I propose to you is a very classical method, I told you, and it's called a probabilistic method because it's just based on data analysis. Apparently, you don't have any physical consideration here. So the question, given that I instead would like to frame my treatment of these models without the context of physically based models, the question is, what is the physical basis here? And I think that we can say that there is already in this method some physical basis, which I will try to describe to you. And we can also say that we can increase this physical basis. So basically, we could couple this method with additional information to increase the physical basis. So let me dedicate 3 minutes to discuss these issues. First of all, what is the physical basis here? The physical basis is implicitly conveyed by the data. So, of course, the data bring with them information on the process, and therefore information on the process physics. So what we can say is that, you know, some people say analyzing the floods in this way is like analyzing nuts. No, it's not like analyzing nuts. It's different because the data here bring physical information on the flood process. So it's something that is implicitly included. On the other hand, it's possible to include additional physical information. How to do that? Look, this method basically is based on extracting information from the data, extracting the physical information from the data. And how is this physical information extracted? By computing two statistics, the average and the standard deviation of the annual maxima. That's it. So what this method uses is just two simple statistics. Okay, now let's suppose that you have information through alternative methods on the average value of the annual maxima. You may have this information. Why is that? Because you may have, for instance, information on a regional level. You may know that in the given region, in the given wide region, the annual maxima can be estimated through alternative methods, the average of the annual maxima. So basically, you may know, and this is indeed true, for instance, in Italy, for each administrative region in Italy, in the past, relationships were provided for estimating the average of the annual maxima depending on the catchment, on physical behaviors of the catchment. So the catchment area, the catchment shape, the catchment slope, the catchment geology. This has been an attempt that has been done in Italy to provide, again, for each administrative region, this relationship. I say again, to estimate the average of the annual maxima. Why we had this idea? Because in some regions we didn't have many observations. And in some cases you may have no observations.